I just want to show you how powerful this is. This is at 240 volts, 1 hertz. Watch this. Look how much kicking it is at 1 hertz. It's just tremendous torque being generated in this motor, a 6-4 arrangement. If we just go up to 2 hertz, which is twice as fast, 3-phase power synchronous motor, U sticking torque between V and W. I'm about to break my finger off. I think it's about to kick me. What we're going to do today is explain as simply, precisely as possible the advance we've made in the science of magnetic motors. We're not going to talk about one-phase motors or DC or AC. We're talking about 3-phase motors, which is the most common type. The most common type of motor is called a squirrel cage or copper induction motor. Magnets rotate around a squirrel cage of copper bars, and the current induced by Lenz's law lets the rotor of the squirrel cage turn along with the rotating magnetic field. If it lags behind like a dog on a floppy leash, not entirely satisfactory. Much better to have a magnet motor where the magnets are precisely aligned with wire coils. Now it's easy to do that. The magnet NS will align with the wire coil NS, just sit over and attract to repel quite easily. But how do you make a magnet go sideways, what's called for torque? How do you make a magnet go sideways? So that's the fundamental thing we've discovered. 3-phase power. Typically you have 3 coils, U, V, and W. Now if we have our friend, the first magnet here sitting on the U coil just like before, it turns out between the V and the W coils, we put another magnet precisely placed, and it gets pulled very strongly clockwise, not anti-clockwise, clockwise. That's why we call this VW torque. It won't go the other way. Now if you want it to go the other way, we can either reverse the current with a keep an NS magnet, or we keep the 3-phase power. Here's our friend the U magnet. We simply make it an SN magnet, and now to go anti-clockwise. And that's the fundamental principle behind the new science. We can have half the motors on Earth can be replaced by this principle. And what are called synchronous motors, which are magnet motors, they can't even start them now. And this is exactly how you can self-start them without going to a lot of fuss. Discovered here, February 2020. Thank you very much. Next we're going to do a simple explanatory video. We have 6 wire coils, vertical, wired up as U, V, W, U, V, W, using 3-phase power from this simple little device at 1.2 hertz. At this speed, it's 1 hertz, 1 second between magnets, each of 4 magnets. 6 wire coils, vertical, and 4 magnets, or cube magnets, with all the poles pointing out, facing them. Each hertz is 1 second between the magnets passing there. And what we want to do now is analyze the forces between magnets. If we go to 2 hertz, you see it's going twice as fast. Half a second between magnets passing here. We go to 3 hertz, going 3 times as fast. We go to 4 hertz, a quarter of a second between magnets passing here. If we go to 5 hertz, we've got to hold the top of the pole now for stability. It's 1/5 of a second passing there, so it's the RPM is linearly proportional to the speed in hertz. If we go to 6 hertz, it's even faster. I can't go very fast because I'm holding the central pole for stability. If we go to 10 hertz, watch it spin. So now what we want to do is, we know how it spins. We want to analyze the forces very quickly. Now for that purpose, we'll go down to 1 hertz. We have U, V, W, 6 coils, U, V, W all hooked up in a row, standing vertical and 3-phase power at 1.2 hertz. We have 6 vertical coils. We have 4 cube magnets, neo, pointing out to each one. Now if we stop any neo magnet, it's hard to do. There's so much torque. You can see there's just tremendous clockwise torque once per second. I'll explain more where this torque comes from, but this is just unprecedented in that range of synchronous motors. Look at that, it's like a horse kicking me. Let's go to 2 hertz and see if my hand doesn't get taken off. Oh, it's like the horse kicking me. Look at that torque. 3-phase power synchronous motor. Repeat, we've got 6 wire coils and 4 neo magnets arranged U, V, W all around. And what happens is, when a U magnet goes here and sticks, there's a big torque between V and W that pulls it sideways. So we have a sort of a synchronous motor combined with a linear motor. Now I just want to show you how powerful this is. This is at 240 volts, 1 hertz. Watch this. Look how much kicking it is at 1 hertz. There's just tremendous torque being generated in this motor, a 6-4 arrangement. If we just go up to 2 hertz, which is twice as fast, 3-phase power synchronous motor, U sticking, torque between V and W. I'm about to break my finger off. I think it's about to kick me. So the torque of this motor itself starts, and the torque is just tremendous. Very interesting indeed. And it spins up quite easily. This could be used for electric cars, airplanes, everywhere. Discovered here. Thank you very much. Study the effect of back EMF in this little device very easily. UVW, UVW, 6 coils with 4 magnets inside. UVW leads, all disconnected so no current is flowing. In that case, if we spin the magnets, it spins quite freely. If we short the 3 leads UVW, connect them all together, you get electrical braking almost immediately. And here's it spinning just due to mechanical forces. And that's the slowdown. So we're going to short all 3 UVW leads together with a blue tape. And we give it a spin, and we see the thing stops almost immediately due to electrical friction. You can also check for back EMF quite easily with 2 magnets pointing out and 2 magnets pointing in. UVW, UVW, 6 wire coils, 4 magnets. Here we have the U lead, the V lead, and the W lead all disconnected. So when we spin, it'll only slow down by mechanical forces. That's just slowing down by mechanical forces. Next, when we put all the UVW leads, wire them together so current is shorted. 6 wire coils, we have 4 magnets, 2 out, 2 in. Now, with electrical braking, the thing will hardly spin. This is also suggestive of torque. So both arrangements, 4 magnets out or 2 magnets out, 2 magnets in, show very high electrical braking, and that's also typical of a very high torque motor. For the record, we'll just record how much voltage and current we get by hand spinning this little device with different wirings. We have 6 coils U, V, W, UVW, about 1,000 turns each of 0.5 millimeter wire. Any of those coils alone, UV or W, by hand spinning gives you about 1 to 1.1 volts AC and about 40 milliamps AC, say that coil alone. If we take UV pairs, that pair or that pair across there, instead, hand spin it with 3-phase wiring, we get about twice the voltage AC and about 50 milliamps, and it goes down to 0 almost immediately as the rotor brakes very quickly. So clearly we're involving both of these 3 coils in the 3-phase arrangement.